All right, welcome to the after work video. Exciting video. Yeah, this morning I did a shorter one. I believe I was on use case 8. It looks like I still have the browser, or I still have the Jupyter notebook running, so that will be good because then I won't have to go back and. Oh yeah, we had an error there, but it didn't affect the graph where we left off. So I should be able to come back here and just run from where we left off. So let's try to close out this use case. The next step is to decide how we transform our log in numbers. In the previous use case, we have used the bag of words technique. Here, such technique is not an option because you inherently lose any sense of sequence or the words or characters in doing that. Therefore, we need a different approach. The first decision to make is what our token is what is our token. What is the unit that we will turn into numbers? Is it a word? Is it a character? Is it a n-gram? So n characters or n words in this meaning. Meaning your token can be all sorts of different things. So you need to define that. The most common approach is to use words and build a dictionary of words. In this case, I will be using the character as the token. There are two reasons for this. Number one, so the character would be in the word token, we would have 1, 2, 3, 4, 5 tokens because each character is a token. In this segment here, our token and what we would have these special characters included in there as well, as far as I know. There are two reasons for this. Number one, this is an experiment, so why not give it a try? Number two, what you choose as a token will determine the size of your dictionary. If you choose words, your dictionary will be very large, and in this case, with logs, there are many different words and codes. Yep, we could clean some of that as we did earlier. If you choose characters, the size of the dictionary is much smaller. Whatever you choose will impact the size of the matrices that represent a log. Since the choice has been to use a character as a token, we will first transform each log into a list of characters. Alright, so syslog message, number of tokens in log, size of dictionary. Alright, transforming that. Now let's build our dictionary by extracting all the different characters presents, and this is meant to be present, I think, in our log dataset. There we go. The length of our dictionary, C_vocab, is 68. That means the matrices will represent each log. The matrices that will represent each log will be 68 by 208. Now it is time to create the data structures that will allow us to translate from each token, each character, to a number, its index in the dictionary, and vice versa. First, we will translate the input logs into numbers. Once we get a log prediction, it will appear in the form of numbers, and we will use the reverse dictionary to get the corresponding word. So let's create the mapping dictionaries out of our complete vocabulary. Now you have two data structures that will make it very easy for you to translate from character to number and from number to character. So here's the first one, number to character dictionary, and then character to number. Very important. These dictionaries are your decoder ring for everything else that comes ahead. If you train your models, but you lose your dictionary variables for some reason and have to recreate them, your models will need to be trained again because the indices will not match. Therefore, I highly recommend that you save your dictionaries in files and load them when needed again, and keep the dictionary as stable as possible. If your data set changes substantially and your dictionary is invalid, then you will need to train your models again. Here is some code to save and load the dictionaries to and from files. There we go. There are preloaded dictionary files in the notebook, same files as above, if you prefer simply to load them instead of generating new ones. Now that we have the dictionaries, it is time to use them to encode the logs based on the dictionary. Effectively, each log, which at the moment is a list of characters, will become a vector of numbers. The entire log list now becomes a matrix. Alright, so let's try to get that far. Oh, so we've got some errors here. That's not necessarily a bad thing. Troubleshooting is good. Okay, so this is this is saving these important dictionaries. Okay, so we've got we got a key error here. So yeah, it didn't populate correct. So I guess it makes sense to spend some time on those errors. Okay, so I think it's down here. Yeah, so all right. But moving on in the meantime, we now have training arrays with the following size. Due to compute resource constraints, I will not be using all the logs for training, but only a portion of them. This may definitely influence the fact that the results will not be great, but the matrices would be too large to keep them in memory. There are methods to avoid this, such as the so-called incremental training, that we will use in the next use case. However, in this case, I will work under the assumption that all my data will be kept in memory. This is an important factor to consider as we address more complex and higher scale use cases. While we have the tokens expressed in the form of numbers, our data representation is still not adequate. Let's explore 3 consecutive positions in the dictionary. All right, and I'll check back on the notebook. All right, yeah, so this one takes a few minutes for sure. When an ML model receives a number as an input, for example, a 10, it is not the same to receive an 11 next or to receive a 500. This may sound obvious, but it relates to the fact that among numbers, there is some sense of order, closeness, or distance. That means 11 is closer to 10 than 500 is. However, in our context, those numbers represent characters, tokens, which in practice are not closer to each other in any sense. Yeah, so if you have a category, you want to label a picture of a dog or a cat or a hamster, I think it's pretty self-explanatory what that means. At least we cannot easily argue that blank is closer, or an underscore character is closer to a capital C than a capital W is. Yeah, like maybe you could, in the alphabet, it's closer, but how meaningful is the alphabet when it comes to producing language, when it comes to selecting which character matters? It's more meaningful that you would know the difference between vowels and consonants than the alphabet. So if we were to feed our ML algorithms with the data as it is, we may be misleading it because there is an implicit ordering relationship that is coded, which is not adequate. So yeah, so now we've assigned we've made these related to each other in a way that they're not. If it was a mapping of vowels to consonants, that would be better, but it's just a random mapping of random characters. That is the reason why categorical variables, like in this case, the token index, need to be one hot encoded. This basically means binary encoded in a vector where each position is represented by one dictionary entry. For each token, all positions in the vector will be 0, and only one will have a 1. With this approach, we have eliminated the sense of ordering that we had before and will not generate misleading results. On the contrary, this approach generates much larger matrices of very sparse input data, which is something that does generate issues. Some might argue that this causes more problems than the implicit ordering of the dictionary index in number. I prefer to one-hot encode, but depending on the use case, it may be necessary to evaluate and try the two alternatives. The following function will help us one-hot encode the training matrices. Alright, so let's check back in on the notebook. Alright, everything looks good there. We just got some warnings. Warnings can be ignored. Now, we do get this same error here. So, not sure what that error is. It's a valid index error. So we don't have. We're trying to reference a index that's not valid. Yeah. Interesting. But it doesn't break anything else from running. So. And the weird thing is we do see index 0 there. So I don't know what's going on. Okay, so here's that same error. It's a type error. It's happening in the label logs, and then when we do the, so it's line 5, 1, 2, 3, 4, 5. When we do the dot append, we can't append so it looks like this here. This is a it's not an iterable, so it's a float. So let's take a look at that. So we're going to do print log list I, and then run the cell again. Okay, and then let's print a new line character as well. Okay, so yeah, we've got 2 of this. So it's going to be we're going to append it to a string logs. The character. So for character in log lists. Okay. You know what we can do is I think all we need to do is just have it be a string, convert it to a string, and do it that way. I think that should work. Because it looks like it's getting, yeah, I don't know what's going on there, but if it can't append it because it's not a string, let's make it a string. Okay, so same problem. Float object is, oh, okay, you know what? It's because, oh, and we printed off the wrong one. We really want to see this one here. It's not the same, so. Yeah, it's going to be a bit more difficult than that because it's trying to iterate through an object that's not iterable. So it's not just a matter of converting the result of the iteration. It's a matter of fixing the iteration itself. Okay, so now we have it like this. Interesting. It's a float? How is it a float? That does not seem like a float. Does this look like a float to me? To anyone? What? All right, well, let's do a type on it. Oh, you know what's happening is I know what's happening. So, okay, I get it now. So, yeah, if we look at if we print out the type each time, I get what's happening, I think. So I think if I were to do a print out a -1 on that, then we might see a float. Unsupported for float and string. What the heck? Can only concatenate. Oh. Okay. Uh, where does this next log list even come from? Where does that even come from? All right, I gotta take a quick pause. I'll be right back. All right, I'm back. Feeling great. I've got probably about 20 more minutes, maybe 15. So yeah, let's put it to use. So we're troubleshooting this one. Now we had that other problem. Maybe that has to do with this. Let's actually go back and check that. So no, this just has to do. Oh, you know what? I think this does have to do with it because we're defining this next logs for device. So let's see where this pops up. Nope. Okay, so this is. I remember there was a next in there, but it's a bit different here. Okay, next log list. So it's different. It doesn't have to do with that cell apparently. So let's do this. Let's do. We're gonna print. Let's print log list I as the first thing that we do up here. Okay, so now we've got one entry here. We've got another entry, and then now we've got a type error. Float object is not iterable. Yeah, so it's happening on this one, I think, because yeah, it'll loop through. Then it'll print it out, and we see this one was fine. And then it will loop through to the next one. So I think, why is it getting a float object? So let's do this as well. Let's do a print type log list I to see if we get a float object. Okay, so this is even weirder because we can see that these are strings, but yet there's something that happens Oh, and you know what? It's the wrong. It's the wrong one. We don't really need to see log list. We need to see the other one. Okay, so log list. This seems to be working fine. We can see the error. The error is at the label, not the training. So let's. I mean, first of all, I don't even know where this next log list came from. Let's try to find that. Okay, so it came from here. Let's just start by printing out next log list up here. All right, and then comment everything else, and there we go. Okay, so here's the here it is. Yeah, so we've got some values here. Yeah, so and let's do this. This should be kind of eye opening. So we're gonna take it out of a list comprehension, and we're gonna do for car in next log list. Okay. And we're gonna do print car. Okay, so now we can see we do have characters here, but it looks fine to me. Let's try print type on car. Oops, and I have insert activated, so deactivate that. Okay, so now yeah, they're all strings, but then we get a float object. Well, you know what? Let's do this. If type car equals let me try this. So type car equals str. Does that work? All right, so well, let's try it like this. Okay, so we've got an incomplete input on line 13. Oh, yep, forgot a parentheses. Okay, so we still got that problem where a float object is not iterable. So obviously, it seems like man, that's so weird. But it's not a float object. Wow, that's really, really weird. Man. Especially since I explicitly only do it if it is a I only do it there. All right, let's go really nuclear. All right, we're gonna do the nuclear option. There we go. Now the cell will run. There we go. So, all right, well, let's just go with that. That's the nuclear option. Hopefully it doesn't cause any problems. Looks good. So we've got 68 for that. Hopefully we can get some sense of... Okay, so we've got the O. Now this failed last time. And it succeeded this time. So it looks good. Training array that shape. So I think we're training array b.shape. I think we're caught up now. Oh, we have to get down here. So let's go down there. All right, so that's a cell that's taken a while. So let's leave that to work and make some more progress in the reading. Now our matrices are 3D matrices where the first dimension represents each observation and the second and third dimensions are the matrix that represents the log. 208 characters, each represented with a 68 length vector of zeros and only 1, 1. There we go. So this 208 number and the 68 number are probably pretty important, so we'll see if those match once that is complete. The final step before we proceed to the training process is to split our data between training and testing. We will do a simple split of arrays under the assumption that they are quite randomized already and would be a good enough approach. You may use other more sophisticated techniques for this. There we go. Time to choose our model to predict the next log. Since we are dealing with sequences of text, the first intuition is that LSTM may be a good approach. Also, we have one hot encoded log messages, so the input is actually a sequence of vectors, which fits quite well with LSTM nature. As it is a matrix, we could think of a convolutional neural network. We could think a convolutional neural network could also do the job, since they are good at dealing with matrices. We are also going to use LSTM. We are going to use LSTM for now. In particular, we will use bidirectional LSTM. This means the model can take information both forward and backwards from the sequence to learn information. Since it is a text, it is frequent to use bidirectional because the model can learn more about the reasons for a specific token to be there. A character in our case, but a word in most of the cases. As mentioned in the theory, there are other more advanced ways to gain context, such as attention, but I will not be using them. They exceed the compute resources available in my setup, and we do not need to go that far for now to understand and address this use case. The following is the structure selected. All right, a visual representation is as followed. So this would be a great stopping point. I'm very quickly running out of time. Let's do the classic tried and true of having ChatGPT read this out, and then hopefully we can get we can get the results in the notebook. Oops. There we go.
A diagram of a neural network architecture involving LSTM, long short-term memory layers, which are commonly used in sequence modeling tasks. Here's a breakdown of the diagram. Input matrix. The input matrix has dimensions n times 208 times 68 n times 208 times 68 n times 208 times 68. N represents the number of observations. Each observation is a vector of size 208 times 68,208 times 68,208 times 68. LSTM layers. The input matrix is fed into a series of LSTM layers. The first LSTM layer processes the input and outputs a matrix of size 128, 128, 128. This output is then fed into subsequent LSTM layers, each reducing the dimensionality further, e.g., from 128,128,128 to 256,256,256, and so on. Dense layers. Following the LSTM layers, there are dense, fully connected layers. The final output from the dense layers is a matrix of size 68 times 20,868 times 20,868 times 208. Output matrix. The final output matrix has dimensions 68 times 20,868 times 20,868 times 208. This architecture seems to process sequence data, where each sequence is represented by the input matrix. The LSTM layers are used to capture the temporal dependencies in the sequence, and the dense layers are used for further processing to produce the final output matrix. If you have any specific questions or need further clarification on this diagram, feel free to ask.
All right, so I don't, and it looks like the code ran successfully. We got all the same values, so I am out of time. So thanks for watching, and see you in the next one.